In calculus, we're very interested in studying motion, or the changes in position of objects. And now that we know about how to measure angles, we can talk about two functions that help us to break down motion on a circle. So this is a great website here that you can use to check out some neat applets that they've made. The one I'm going to look at is this Ferris wheel one. So imagine you're on a Ferris wheel and you want to think about the motion. Now this Ferris wheel is turning counterclockwise to us. That's the way we like to turn things as mathematicians. So somehow we didn't get the memo about going clockwise with everything. But looking at this Ferris wheel, imagine that you're in one of these gondolas and you're just going to go circling around. Notice that two things are going to be happening. Your horizontal position is going to be changing. Remember, horizontal is with the horizon, so your left and right position is going to be changing, but also your vertical position will be changing. We're going to use two functions called sine and cosine to break that motion up. So just to sort of illustrate what's going on, let's just focus on one particular gondola. So let's look at this red one here and just follow as it goes along. Now think about, as the wheel turns, what happens to the horizontal component and what happens to the vertical component. So if you look at the horizontal component, as this turns, I'll just try to keep my mouse underneath it all the time. You see how the horizontal component is decreasing until it's right over the hub, and now as we continue on, we end up as far back as we're going to get, and then we start increasing again as the angle turns, or as the Ferris wheel, as time goes on, right? So we have a horizontal component to the motion. We can also look at what happens with the vertical component. So to look at that, I'm just going to rotate the Ferris wheel here a little bit so you can just study the vertical without being distracted by the horizontal at the same time. So here comes our Ferris wheel around. Let's see, before our starting position was right here. So if we started out right here with our gondola in standard position with an angle of 0, we go up. We reach some maximum point. And as the angle continues to increase, or as time goes on, we come back down. And we get to our lowest point, and then we come back up to where we started here after having made a complete turn. So we're interested in taking that circular motion and breaking it up into two components. And we're basically making two functions that depend on the angle. So if we have some angle here, of course if we do it in radians, then, and this is the unit circle, then this is our angle alpha. It's actually this distance along the circle. For that angle, we can look at what's the vertical that goes along with that angle and what's the horizontal. So the vertical we would call the sine of alpha, and we just drop the e to abbreviate it. So we're thinking we have a function, and the input is the angle that we've turned, and the output is what's our vertical component. And the horizontal we could call the cosine of alpha here. This is only on the unit circle. Of course, if you scaled everything and made the circle bigger so that this distance was r, then all of these would become proportionally larger. So this would be r sine alpha, and this distance would become r cosine alpha. Everything just gets stretched by that same factor r because everything's going to be similar. Okay, so we've got our sine and our cosine. Now we can actually figure out what the sine and cosine are. For a few values of alpha, it's pretty obvious. Let's see, here's our angle alpha, and then we can think, okay, what's the vertical, the sine, and what's the horizontal, the cosine. So for example, if the angle is 0, so alpha is 0, then your initial and terminal rays are aligned. That means that the vertical component is 0, and since this is the unit circle, then the cosine is just going to be 1. And if we turn all the way up here to pi halves, then we can see that our vertical is 1, we're all the way up at the top, and our cosine is 0. Keep turning to pi, so over here at pi, you can see that our vertical is back down to 0, and now we're going back 1, so the cosine is negative 1. Keep turning to 3 pi halves, so that's go 3 pi halves along the arc, and you'll be to here on the unit circle. And there you can see that the horizontal is now vertical, and there is now 0, and the vertical is -1. And if you turn all the way around to 2 pi, then you're back to the same situation where the angle was 0 as far as the sine and cosine are concerned. The sine is back to 0, and the cosine is back to 1. Okay, and of course these angles might have ones that are more familiar to you in terms of degrees. 0 degrees and 0 radians are the same thing. Pi halves is 90 degrees, 180 degrees, 270 degrees, and 360 degrees. And just put those in since we're familiar with those. So given that, we can see that we have an input, the angle, and then this sine function, this is the name of the function, and this is the input. The sine function has various values, always between -1 and 1, because sine and cosine are defined on the unit circle, the circle with radius 1. So the most you can go up is 1, and the most you can go down is -1. So sine just gives you a vertical distance on that unit circle, somewhere between -1 and 1 always. And cosine, since the farthest you can go forward is 1 and the farthest you can go back is -1, cosine also gives us values between -1 and 1. So we have these two functions. We could ask about their graphs, and we have enough data points that we could probably draw a reasonable sketch for these. We know that if we're going to draw the sine, that the sine of 0 is 0. Pi halves, though, the sine of pi halves is 1. The sine of pi was back down to 0. At 3 pi halves, that would be 1.5 pi. Then the sine was -1, and by the time we got to 2 pi, we were back here. So we have a function that went up, right? So we went around the Ferris wheel, we go up, and then we come back down to the middle, then we drop down to the bottom of the Ferris wheel before we come back up to our starting point along the x-axis. And I should be a little bit careful here. This isn't actually vertical. Sometimes students think these are like two half circles, but of course on a circle, on the ends of a circle, you're actually vertical, and that's not the case. So this actually has a slope of -1, and that has a slope of 1 if you measure it at those particular points. So they're not really vertical. We'll find out more about that later on. For the cosine, let me use maybe a different color here. So make that one red. Okay, for the cosine, we saw when the angle is 0, you're all the way forward, so the cosine is 1. When the angle is pi halves, your horizontal component is 0, so the cosine is 0. When the angle is pi, you're all the way back to -1, as far back as you can go. And when the angle is 3 pi halves, you're back to a horizontal component of 0, right? You're either forward or behind the axis of your Ferris wheel. And when you come back to 2 pi, the cosine is back up to 1. This actually gives you a graph that looks something like this when you plot it. I'm asking you to kind of trust me on the details, but this is the graph of cosine here, and if I go back to my original color, then this is the graph of the sine. And I hope you can see that this picture would just repeat, right? As you continue to wind along, you just get bigger and bigger angles, and so you would go up and down and back and so on as you went along this. So the graph of the sine would repeat. You could even use negative angles and go backwards, right? So negative angle would just mean that your directed angle is back that way. Okay, and so same thing with the cosine. I'll just quickly fill it in, although it should be red here. Okay, so these functions repeat themselves, and it takes an angle of 2 pi before they start to repeat, so we say they're 2 pi periodic. It takes 2 pi for them to repeat. Now, to help you see the relationship between circular motion and the graphs of sine and cosine, we have this little applet that shows as the angle increases, and you see the sine go up and then come back down and then go up again. This happens to be in degrees, but you could always change units to have it in radians, which would be the most common thing. Let me go through that a little bit more slowly. So the angle increases, then so as you've turned around more, right, then gradually the height increases until you reach the top, and then the height comes back down again. And you're back on the level before you dip down below the level of the axis and come back up. Same kind of thing. This could just keep repeating as you go on, right? Okay, and you get a function that goes on infinitely in both directions, really. It's periodic, repeating every 360 degrees or every 2 pi radians. So, similar thing for cosine. In this case, we have it drawn so that we're tracking the horizontal distance, and as the angle, initially you're all the way forward, right? And as the angle increases, you go back, and then you come forward again, and you start over. Now, usually when we draw a graph, though, we have the input axis. In this case, the angle should be horizontal, and the output should be vertical. So we could always rotate it up, and then you see the graph of cosine, just like we had drawn it before, right? Cosine, you start at the top, go down, start all the way forward, come all the way back, and then all the way forward again. Sine, you start on the level of the axis, you go up, and then you come back down, you dip to the very bottom and come back to where you started before you go around again on the Ferris wheel.